All right, good afternoon. Let's get started. Turn the volume down a little bit. Last proper lecture in the series, so we do reinforcement learning today. And then next Thursday, the last lecture will be about a review. We will review all the subjects, all the things we've talked about. If you have any questions, I'll send an announcement later as well. But if you have any questions, anything you'd like to hear explained again, anything you didn't quite understand, feel free to send them to me or to post them on Canvas, and I will make sure that I spend some time on that in the last lecture. I haven't decided exactly what I'm going to talk about yet in the next lecture, so if you have any requests, please send them to me. But for now, the last bit of new information, reinforcement learning. When I started this whole series of lectures, in the very first lecture, in Introduction to Machine Learning, the very first thing I did, or the very first thing we did, was to take this idea of an intelligent agent, of an artificial intelligence, something that lives in a world, that learns about the world and interacts with the world while it's learning, and things like that, to take that whole complicated idea and to massively simplify it by taking it offline, by turning it into offline learning, where we have a data set and we learn once from the data set to create a model, and that's it. That's our machine learning. It's called offline learning, and that's what we've been doing for the past 7 weeks. But sometimes you cannot simplify your problem like that. Sometimes your problem is actually about learning to act in the world. And in that case, reinforcement learning provides us with a framework to solve that. So reinforcement learning is all about taking agents that have to behave in the world and learn in the world at the same time, and constantly update their model in this feedback loop where the world provides them with information and they learn from it. So as you can imagine, that's a lot more complicated. And I don't have a lot of time to go into it very deeply, but I'll just try and give you the gist of it. So this is the plan. I'll start by talking about reinforcement learning in general. What is it? What do we mean by it? What's the framework? Then I'll discuss a few approaches for reinforcement learning, and I'll focus on the approaches that allow us to do reinforcement learning using these deep neural networks that are now so fashionable. And I will try to describe 3 approaches: random search, policy gradients, and Q-learning. So the break will probably happen somewhere here. And then finally, I would like to talk to you about probably the most important news story, not just in reinforcement learning and not just in machine learning, but probably in AI of the last few years, which is the spectacular result of AlphaGo, this Go machine that DeepMind built to beat the top Go professional, one of the top Go professionals in the world, which was a big deal. So I'll talk briefly about why that was a big deal and about how they did it, and they did it using reinforcement learning. So that's what we'll finish on. So lots to go through. So let's start with reinforcement learning. So we're not taking things offline. We have an online system that learns as it interacts with the world, which, as you can imagine, makes things a lot more complicated. So the framework, the way we abstract this, to the extent that we abstract it, looks like this. We have some environment, and we have some model. And the model finds itself in a state, which is just the state of the world. We'll look at some examples later. And it observes that state, and it decides to take an action. And after it's taken an action, the environment tells it, you are now in this new state, and you have received this reward. If it's done something good, then it gets a positive reward. If it's done something bad, it gets a negative reward. So this is like winning a game might be a positive reward, losing a game is a negative reward, dying if you're an agent, crashing if you're a self-driving car, might be negative rewards. And then the learner looks at this process and updates the model while the model is learning and while the model is taking actions in the world. So it's not much of an abstraction, but it's still, this is how we abstract. So first thing to note is that if I want you to do an offline learning problem for me, all I have to do is give you one big table with the features and the target value. I give you a CSV file, right? That's easy. If I want you to solve a reinforcement learning problem for me, I have to code up an environment and I have to give you that environment. But it's a lot more difficult. So I have to define basically a simulator for the environment, or if it's a computer game, I can just give you the environment. This is why we like to abstract things away to offline learning, because things are so much more simple. There are standard problems available. We'll have a look at a few of them. I didn't include it in the slides, but if you Google OpenAI Gym, then you can actually find a whole load of libraries, Python libraries, where you can learn to play Doom, which is a very old first-person shooter, probably before your time for most of you, unfortunately. You can learn to play Pong, and you can learn to control little creatures walking around in the world. So there are people who have coded up lots of these environments that we can use to benchmark these tools. Let's start simple. So most of the very simple reinforcement learning problems, when we try and explain the basic principles, they look like this. So we have a basic, here we have 6 states, which corresponds to 6 areas of a room. And we have a robot, something like maybe a floor cleaner or somebody exploring the room, who gets dropped in one of these parts of the room and has to move around. And if he starts here and moves here, then there's no reward. Nothing happens because he hasn't found anything, he's just moved around. Maybe a slight negative reward because he's used energy, depending on how we want to model the problem. And then he has to move around until he hits this point, and then he's found the goal, and then the game or the simulation ends, and the robot gets put back here. So if it moves into this section here, it gets a reward, which we can set to +1, because the actual value doesn't matter, only the relative value. So if we set all of them to 0 and this to 1, then that's enough to learn that this is a good move, or this is a good move. So it's fine, and then when it's found the goal, we reset the world, we drop the robot in another spot, and keep going, and then the robot learns how to navigate this world, which obviously is not a very interesting problem, but we have to simplify it this far in order to understand the basic principles. So most of the toy examples that we use to explain the principle will look like this. Another thing you can model with reinforcement learning is 2-player games, where you have specifically 2-player games like tic-tac-toe, or more complicatedly chess or Go, where players move in succession. So we start with an empty board, then player 1 has a certain number of moves, then player 2 has a certain number of moves, and player 1 moves again, and so on, until at the very end, one of the players has won. So the important thing here is that these are actions, of course, so the state is fully described by the state of the board. If I give you in tic-tac-toe all 9 values of the board, you have the full state, and I have to tell you whose turn it is. Actions are simply the moves, the legal moves that the player is allowed to take at that point. And the reward is always 0 during the game. So if I move like this, if I put a cross or a circle in one of the squares, the reward is always 0 until I get to the very end, where we can decide who's won. And there, you get your reward of +1 if you've won, or -1 if you've lost. Because the rest of it we want to learn. Whether or not this is a good move, we want to learn from the information from way in the future. So that's the basic difficulty of reinforcement learning, that this reward comes so much later than when you decide to take your action. We'll come back to that. One more example is, I think there's some sound here. Okay, interesting sound. So here we have a slightly more complicated problem with slightly shorter time slices. So your actions are have to happen very quickly. And your state information is a lot more complicated. So this helicopter is flying completely autonomously. It probably has a camera, some sensors, artificial horizon, stuff like that to measure the world, measure its state. And it has to map that very quickly to actions on its rotor and tail rotor, I think are the actuators. So it only has 2 actuators, 2 things it can change. But based on its state of the world, it has to change those very quickly. And it's very fickle. So if you want to fly upside down with a helicopter, apparently that is very, very difficult. It's very unstable. So the slightest change will spin you out of control. So you need to react very quickly and in exactly the right way. I've never done this, but apparently it's very difficult to fly like this. So, and in Stanford, they managed to do this autonomously and then to tweak the reward function a little bit so that it actually learns to do tricks like this into a tail slide. So ideally here, you would want no rewards except when you crash. So if you want to model this as cleanly as possible, you just let the helicopter fly, and only when it crashes, you give it a negative reward. And that would be your first training loop to keep it to stay up as long as possible. Probably they gave it some intermediate rewards and they tweaked it a little bit, because that's probably slightly too difficult to do here. But in sort of ideal setting, that's what you want to do. It's another example from DeepMind, that people who gave us AlphaGo. This was their big success before AlphaGo, where they took some Atari games, which is, yeah, if Doom is before your time, then Atari is way before your time. It's even slightly before my time, probably. But they're games that look like this. You used to buy these little computers and you would play them. You would hook them up to your TV, and they would look like this. You would get a very low resolution screen and a little joystick with 8 directions you could push it in. And you would play a game like this. This game is called Breakout, which you've probably played. And you can see the idea of the game, right? You have to control the paddle and you have to bounce the ball up to the bricks. And the reinforcement learning system that we're looking at here just looks at the screen. So it only gets the pixels as information, and it gets the actuations of the joystick, so pushing the button or moving the joystick, as output, as actions. And the reward is always, yeah, the video is slightly ahead of me. The reward is always this part of the screen. As you can see, after 240 iterations, what it's learning to do now, it can play pretty well, better than I could. But it's learning to dig a tunnel here, and once it's done that, it's learned that it can relax and the ball will bounce all the bricks away by itself. And the nice thing of this, nice thing here, is that they've solved the problem on quite an abstract level. They haven't really told the system anything about Breakout. They've just given it a video screen. So they've basically told the system what an Atari controller is, or an Atari simulator. But if you pop in another Atari game and you say, well, this is the score, then it can learn to play that Atari game. So this is what they did. They learned to play about 32 Atari games just from pixels directly to actions, using a neural network in between. Give that away. So that's some examples of what you can do with reinforcement learning. So let's now start exploring what it is and how it works. We need some notation first. So we get a reward for every action we take. So if we're in state S and we take action A, we get some reward and we call that RS of A. It might be 0.01, might be anything. But the higher, the better. So this is a bit of a cultural thing, but in reinforcement learning we talk about rewards. In supervised machine learning we tend to talk about loss. It's just an arbitrary function. Here it's the higher the better. In supervised learning it's the lower the better. It's just how these two fields evolved separately from each other. Then we model the state transitions, which is basically the way the world works. So if I'm in state S and I take action A, I end up in state S prime, and the function D gives me that transition. It tells me, so function D is my environment. It tells me, or part of my environment, it tells me what state I end up with if I take action A in state S. So the functions R and D together are my environment. Then my model is a policy, what we call a policy, which is basically the function that maps states to actions. So if I find myself in this state, I will take this action. That's a deterministic policy. It's the simplest thing you can do. And this is what we learn. So this is what we choose. This is what is given as the environment, and this is what we choose. And you can also take, if you want to make things a bit more flexible, you can learn a probabilistic policy. So given that I'm in this state, the probability of taking this action is 0.2. So you get a probability vector of all over all actions conditioned on the state. So this is basic notation for reinforcement learning problems. Two things we're not going to talk about, but that are also possible, are probabilistic state transitions. So if I'm controlling a robot, there might be a slight probability that the wheels slip. So it might not exactly, if it has wheels, it might not exactly do precisely what I want it to do. So there's a slight probabilistic aspect to how it executes the things I do. So in lots of these reinforcement learning problems, you have probabilistic state transitions. So I'm here and I want to go there. So I take this action, and the result is that I'm here with a high probability, but I might also end up here or here with lower probability. So you can model that. We won't go into that today. And you can also model partially observable states. So if you can't see all of your world, like the helicopter couldn't see everything about its world, or in a game setting, if I'm playing poker with somebody, then I can't see my opponent's hand. These are partially observable states. So I can't see these things, so I have to model them. The state part of my reinforcement learning problem is I only get to see part of the world, and I need to model the rest. So the rest is kind of like a hidden variable. So there are ways to do this. We won't go into them. So let's look at this Atari model. Like I said, they trained a big neural network to take us from the input pixels to the output actions. So it's a kind of a slightly weird way they diagrammed it out, but this is basically just a convolutional layer, ReLU activation, convolutional layer, ReLU activation, fully connected layer, ReLU activation, fully connected layer, and then softmax over the actions. So this is basically a neural network that models this function, our policy function. It takes us from the state to a probability distribution on actions. These are all the actions we can take. We observe this, we push it through the neural network, and the neural network spits out a probability distribution over the actions. And then we can sample from this, or we can pick the one with the highest probability, whatever we like, and that will play the game for us. One thing I forgot to mention before we move on. We make one assumption when we model the reinforcement learning problem, which is a Markov assumption, a bit like in the language, the sequence modeling thing, namely that the optimal action in the current state doesn't depend on anything but the current state. So that's not always the case, certainly not always the case. So that's an assumption that might be violated, but in most reinforcement learning we assume that if we see this state, the optimal action doesn't depend on the state we saw before or the state we saw 5 minutes ago. It only depends on our current state, which in a lot of situations is correct. Like in chess, your best option only depends on what you see on the board, not on what came before. And if there is a small dependency on the history, then you can just move that into the state. You can just encode part of the history into the state, and then you still fit this model. That's called the Markov assumption. And that's why this works, why we can just look at the current state of the screen and predict the output, and we don't have to remember anything. So that's how we play a game once we've learned. And that's what reinforcement learning is. So another question is, if we have this model, how do we train it? What should the learner do? How do we determine the weights of this network by letting the system play Atari games? And the big problem here, I sort of hinted at it earlier, is what's called the credit assignment problem, which is that your actions, you take actions and you get rewards, but the reward that you get isn't necessarily a reward directly for the action that you've just taken, but it might be you did something good 50 moves ago, and it's only now paying off. Especially if you're playing a game, you never get a reward. So lots of actions in the middle of your game were really good, were really helpful. You only see the reward afterwards. And sometimes you get continuously updated with rewards. You get negative and positive rewards. The negative and positive rewards are sort of interleaved with the actions that were good and bad. For instance, if I'm driving in my car and I happen to crash, most people, when they crash a car and they're conscious, will brake just right before they crash as a shock reflex, which is a very good thing to do. It might not stop you from crashing, but it will stop you from stop the crash from being a lot worse. But if you look at the reward, the thing you did closest to crashing, which will give you the negative reward, was braking. So if you just look at it naively and say, I'm just going to apply the reward to the most recent actions, then it will tell you the braking was a bad idea. And the getting into your car drunk, that was much further back, that was fine. So that's not what you want to learn, right? So that's called the credit assignment problem. You need to somehow, once you get your reward, you need to somehow figure out which of my actions led me to get this reward, and how do I adjust my network weights that I had at the time for the input that I had at that time. Well, a very simple way to do this, or to avoid this actually, is to use random search. So this is back to the first week. I hope you remember that far back. We talked about a very simple way to search. You just pick a random point. So in our case, if we have a big neural network, we pick a load of random neural network weights. We pick another point close to that original point, so we change our weights a little bit in some direction, in some way. We compute the loss for both of them, or in this case, we compute the reward. So we run a bunch of simulations, we play a bunch of games, or if it's a helicopter, we fly a bunch of flights, and we see how big a reward we get averaged over all those. And if the new points are better than the old points, we switch to the new setting. It's random search. You're sort of taking random steps through your model space. And the surprising thing, this is quite recent research, right? It's long after, 2 years after AlphaGo and 3 years after the Atari simulator. I think Uber AI, Uber research department did this. They went back to the Atari thing and they tried evolutionary search and random search on it. And this is a game called Frostbite, which is one of the games on which the DeepMind Atari system didn't perform well at all. So they tried 32 games and two of them specifically, Frostbite and Montezuma's Revenge, the Atari, the DeepMind system, performed terribly. And Uber AI went back and they trained them not with Q-learning, which is what DeepMind used, but with random search, this very simple principle. And they got a really good score. They got a system that worked really well. So this is a sort of current trend in reinforcement learning, deep reinforcement learning, thinking that, where we see that a lot of these simple search methods like random search and like evolutionary search actually work much better than the more complicated methods I'm going to talk about now, policy gradients and Q-learning. So if you want to play around with this, it might actually be better not to go too much into the details and to just try something really simple and see what you get. Nevertheless, if you really want to see, look a little bit deeper into this problem, you need some understanding, which will hopefully come from these two other methods. So that's basically random search. So let's talk about policy gradients, which is another approach, where we're actually going to start getting a gradient to train our neural network, or something approximating a gradient. So we can actually do backpropagation properly. So here we have this delayed reward problem. We get a bunch of states, we take a bunch of actions, and only at the end do we get a reward. And the basic idea of policy gradients on a very high level is that we simply wait until we get a reward, and then we go back and we update it. We update all these steps with what we got. So we just say, well, if we win the game, then all of these actions were apparently good actions. And if we lose the game, then all of these actions were apparently bad actions. So we just wait until we get a reward, and then we distribute that reward. We apply that reward retrospectively to all the actions we took earlier. So this sort of contradicts what I said earlier, right? This contradicts that if you're driving in your car and you crash, then some of the actions may have diminished that crash, and some of the actions you took may have contributed to that crash. So the idea here is that if you do this often enough, and for enough examples, if you average over enough scenarios, then it will average out. So in the car crash example, what you would need here, you would need examples of people who didn't brake before crashing. And if you compare that, if you average that, then lots of the people who didn't brake will get a worse negative reward here, and the people who did brake will get a slightly less bad crash. So then on average, the braking will still get a positive feedback, but on average, getting into your car drunk will get a negative feedback. So that's very important. What kind of examples are you seeing? What kind of things are you training on? Because if there's nobody in your training data who ever got into if there's nobody in your training data who didn't brake before the crash, then you will not learn that that's a good idea instead of a bad idea. So let's try and formalize this a little bit. How do we make this more technical? Well, one thing we could do is we could unroll our network, just like we did with the sequence models. We feed a state to the network. We get a distribution on actions. We get an action. We sample an action from this distribution. We take the action and get some reward. We end up in a new state. Feed that to the network, sample an action, get a reward, end up in a new state, feed it through the network, sample an action, and then we get a reward and a new state. And then our total reward for this sequence of actions and states is 1.2. So why can't we just treat this as one big neural network and just backpropagate this reward? What's the problem there? We've seen it a couple of times before. The problem is here, and here, and here. The problem is that we're sampling. We're getting a stochastic output here, distribution. We're sampling from that, and then we take an action. And you can't backpropagate through sampling. You can't backpropagate through that. You can take the gradient of that operation. We saw that already in the variational autoencoder, where we could get out of it with a handy trick called the reparametrization trick. We can't do that here. There's no way to get out of it. We cannot backpropagate through this. So what policy gradients do instead is they figure out a way to apply this final reward that we get to just apply it as the reward to all of these actions that we've taken. And then we sum over a large batch, we average over a large batch of runs, so that these things average out. So that if this is actually a bad action, then there will be enough, we'll get enough bad feedback there. And the nice thing about policy gradients is that they don't just work for reinforcement learning settings, they work for any model you have, where you have this step inside your model that is not differentiable, like sampling. So if we have a big chain of differentiable things that we can do, like the basic neural network layers, and we want to do gradient descent, but we have one step where we have some sampling or we have some discretization or something we cannot backpropagate through, then basically what policy gradients allow you to do is to take at this node, you basically split it out into lots of choices. So instead of one step, you take lots of samples, you get your reward, and you do backpropagation, and you estimate your gradient over this node from the supervision you get from all these branches. Little bit of math just to show you how it works in practice. This is all stolen from a blog post by Andrei Karpathy, which I can recommend if you want to know more about this. So basically, the way it looks in math is we get some function f, which is the end of our neural network, our loss function basically, or our reward function is f. And because we're sampling in between to choose our actions or to do our other sampling, we don't get a fixed reward, we get an expectation over a reward. We get an expected reward because each time we run the neural network, each time we do a run, it ends up slightly differently because of this sampling. So we get an expectation over our reward, and what we want to use to update our weights is the gradient of that expectation with respect to the weights. And that will give us the direction in which we want to update our weights to maximize the expected reward. So we write this out, we just write out this expectation, which is some probabilities. These probabilities represent our sampling. And then the reward summed, weighted by all those probabilities. This is just the expectation written out. Then we can take the gradient inside the sum, which is just the sum rule that we normally use, but using it the other way around. So we put the gradient inside the sum. We add and multiply by px, just a little bit of rewriting trickery. And then we use this definition of the gradient of a logarithm. We fill it in. So 1 over px disappears, and the gradient of px disappears, and they are replaced by the gradient of log px. And then we rewrite this back to the expectation. So then what we end up with is that the gradient of the expectation is the expectation of fx times the gradient of log px. So suddenly, what we have here is this thing which we couldn't compute has been rewritten into a gradient only over the p-axis, which is a gradient only over this node, right? And we take this expectation and we estimate it by taking the average over several samples from this stochastic node. So basically, anytime you take a sample in your, somewhere, if you want to take a sample somewhere in your network, you can't do backpropagation through it anymore, but you can resolve it with this policy, this policy gradient method. It does cost you. So if you have a choice not to sample, it's much better not to sample, or if you can use something like the reparameterization trick, that's much better, because this approximating this expectation with a finite number of samples is much less accurate than just normal gradient descent. Nevertheless, so that's policy gradients. And if all the math confused you, just think back to this example. All we do is we wait until we get the reward, and then everything we did to get that reward we just punish or stroke. So finally, Q-learning. And this is where we really get into the nitty-gritty and some of the details of how to think about these reinforcement learning problems. So I sort of debated with myself whether or not to talk about Q-learning at all, because it turns out that policy gradients are actually almost always better than Q-learning. But still, the theory of Q-learning does give you some insight into what we're actually doing and what we're trying to optimize. And it might well make a comeback in a few years. So I'll still try and briefly discuss Q-learning. So let's start with some notation. So here we really start with the question, what is it that we want to optimize? What is it that we want to maximize? And how do we get there? From that statement, how do we get there? So it's a much more principled approach. And basically, if we have some policy that tells us take this state and this action, then we get, if everything else is deterministic, then we get our future is determined, basically. We are in some state, our policy tells us to take some action, so we end up in a new state, and so on and so on. We can look at that future, we can look at all the rewards we get. Basically what we do is we weigh them by a gamma, which is some value slightly smaller than 1. We take the immediate reward, we value it slightly higher than, we value a reward now slightly higher than a reward somewhere in the future. So every reward in the future is weighted by gamma to the power of how far it's in the future. So 3 time steps in the future, a reward is weighted by gamma to the power of 3. So this is what we want to maximize. This is our, what do we call it? A discounted reward. So given a policy, once we've chosen a policy, this is determined. So we want to choose the policy such that that is maximized. We call that also the value function. So given a policy and a starting state, the value function gives us the discounted reward for the future, and the value function is a function of the state. So it gives us over all states, given that we're in that state, how much do we expect to gain? So essentially, if you have a policy, you compute the value for all the states that you can get to, the best action you can take is the one that gives you the highest value. So it's called the value function. And then the optimal policy is the policy such that for all states the value is optimized. The optimal policy is the policy that gives you, from all states, the highest possible future reward, discounted reward. And the optimal value function is the value function corresponding to the optimal policy. So you get a recurrent definition here. So now that we have this optimal policy, and we have this optimal value function, what we can do is say, the optimal policy is the policy that chooses the action which gives us the highest discounted reward. So I'm in a state, get a couple of actions which will lead to new states. And if I just argmax over the actions, I get the highest discounted to maximize the discounted reward. And I call that the optimal policy. This is just filling in the discounted reward. So here we see this successor function coming in to determine our rewards. It's getting quite slightly complicated here because of all the recursive definitions, but so the optimal policy occurs here twice. And basically, sorry, let me phrase this properly. I argmax to maximize the discounted reward, but the discounted reward depends on which policy I'm using. So if I assume that I'm using the optimal policy, then I can just fill it in here. So this is what the next state, given that I'm in state S and take action A. This is a reward I'm getting. And this is what the policy tells me to do. So in the rest of this sum, I'm actually filling in the optimal policy that I'm defining here. So we're going to resolve that recursive definition later. But first we'll simplify it to make it a bit more clear. So this part of the sum is just the optimal value function that we defined in the last slide. So the optimal policy, so now we have the optimal policy defined in terms of the optimal value function, which is just to take the action that maximizes the direct reward and the expected future reward under the optimal policy. So we have the optimal policy defined in terms of the optimal value function, the optimal value function defined in terms of the optimal policy. And to simplify that a little bit, we introduce a function called Q, which is just this part, which we're argmaxing over. So we call that Q, the immediate reward plus the discounted reward under the optimal policy. And then we can just state that the optimal policy is argmax A over the Q function, and the optimal value is max A over the Q function. Oh, sorry. So now we've the definitions stay the same of the optimal policy and the optimal value, but we've rewritten them in terms of this value, in terms of this Q function. And what that gets us is that now we're going to learn the Q function. The Q function is going to be the thing that we approximate with our neural network or our other function approximator. Let me just see if I can. Right, the second half is not very big, so with your approval, I'll eat into 5 minutes of the break, just to finish the discussion on Q learning, and then we'll have a slightly shorter second half. So we've defined the Q function, and Q function helps to simplify everything. Yeah, we do a bit more rewriting to get rid of this optimal value function and get rid of this optimal policy, and rewrite the Q function in terms of itself. So even more recursion. So we just rewrite this, because the optimal value function we just defined is this max over A of Q. So now we have the Q function expressed in terms of itself as a recursive definition, which might be a little confusing. Certainly I'm starting to get confused. But this is very useful, because this doesn't tell us how to get to an optimal Q function, but it does tell us if we have some Q function, if we just pick any function that takes a state and an action and outputs some numeric value, we can ask, is that a Q function? We just pick it at random, is it a Q function? And it's a Q function if and only if it satisfies this property. So you can take for just, these are all our states. So we have a very simple problem here. We have states A and B, actions left and right. And you can ask for these values, for this function, for these inputs and these outputs, is this recurrence satisfied? If so, then this is the optimal Q function. If not, then not. If you look at the slides annotations, it's actually worked out, and if I remember correctly, this is not the optimal Q function. So that's one algorithm you can do. You can just pick something at random. If it's not, then you can pick another one at random. That's not very efficient. So how do we use this to find the optimal Q function? And let's assume for now that our Q functions are not neural networks, but are just written out like this. But the problem is simple enough that we can just write the Q function out as a big table. What you can use to get from a recurrent definition like this to an actual value is something called iteration. So forget about tables for the moment. If we have a function like this, x equals x squared minus 1, then we have a recurrent definition because x occurs on both sides of the equal sign. Obviously, you can all solve this. This is what we learned in high school, how to rewrite this to solve it. But instead of rewriting it, you can also turn it into an iteration. By turning the equal sign into a left arrow, so it becomes an operation. Let's see, and just to make the example work, make it minus 2. And then I have to start with x is 0. I apply the iteration, so x squared is 0 minus 2. X becomes minus 2. So for x is 0, this equality didn't hold. I apply the iteration again. I square this, which gives me 4. I subtract 2. So I get 2. So again, for minus 2, the equality didn't hold. I do the same thing again. I square this. I subtract 2. So I get 4 minus 2. And I get 2 again. Which means I've ended up at a fixed point. A point where if I set x to 2, and I apply this iteration, then I get 2 again. So if you have a recursive definition like this, with x on both sides, with an unknown on both sides, you can use this iteration method to find a fixed point for which the equality holds, for which if you set x to 2 here, then this x will also become 2, and therefore the original equality will hold for x is 2. It's called the iteration method. And the nice thing is that it holds here as well. So if we use this algorithm, we initialize QSA as 0 for all states and actions. And we loop. We use some algorithm to take some actions. We observe the states we arrive in and the rewards we receive. And then we just update according to this equality. So if the observed reward, the observed future reward, is not equal to this, which it should be, then we set this equal to the reward we observed. And if we keep doing that for long enough, you can prove this, then QSA will converge to an optimal Q function, which will give us an optimal policy. Of course, that only works for tables. So how do we do this if we have a big neural network? We make the neural network implement the Q function. So the neural network now goes from states plus actions to an output value, which is actually the same shape of neural network. So we just read out, for this state and this action, we just read out the Q value here. So actually the neural network has the same shape. And for every time we update, we observe this, we get to this rule in the algorithm. We do the forward compute here, and we compare how much it differs from this value that we've observed, and then we backpropagate that. So the difference, we forward compute to get this. This is what we observe from the algorithm. The difference between these two things is our error, which we can directly backpropagate. Finally, this part of the algorithm deserves some attention. it's usually not a good idea when you're exploring, when you're learning, to use your policy that you've just learned to take the next step. Because what you do then is, if you learn something relatively successful very early on, you immediately start over-exploiting that, and you never start doing anything else. So if you have a very simple problem like this, you start here and you move around a bit and you get, hey, +1 reward here. If you stick with that policy, you will only reinforce it a lot and a lot and a lot, and you will only keep going back to this point. Whereas if you explore a bit more, and you take steps that are not optimal according to your current policy, then you might learn that if you go all the way here, you get a much bigger reward. This is called the exploration-exploitation trade-off in reinforcement learning, which is a very important problem in all online learning. Basically, that you don't want to immediately exploit anything you've learned. You want to manually mix exploration and exploitation a little bit. So what we do here in the algorithm, we take our actions under a different policy than the policy that we're learning. For instance, you might mix your learned policy with random policy, or, well, there are thousands of ways to do this. But basically what you want to do is you want to explore a little bit and learn a little bit. There's not really a standard or an optimal way to do that. When you stop your exploration, basically, yeah. Usually how it works is that you have a fixed training phase, which is just as much training as you can allow yourself. So when DeepMind was building AlphaGo, they had 2 months until their big match against Lee Sedol. So they used their exploration policy as much as possible during those 2 months, and then they stuck with whatever they had then. So that's, you just, like in supervised learning, you have a training phase and a testing phase, and during your training phase, you use your exploration policy. So that's Q learning, which brings us to the break. And after the break, we will discuss how we use all of this in AlphaGo. I'll see you in 15 minutes.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So that's, sorry. Sound as dramatic as the trailer. All right. So that's a trailer for a documentary called AlphaGo, which is about this DeepMind system and what they did. It's just to show, firstly, to wake you all up. Secondly, to show, well, to give some indication of how dramatic an achievement this was, this AlphaGo thing. They make it slightly more dramatic than it actually was, because it's a movie, so they slightly over-dramatize it. But it is a very good documentary. I can recommend it. So let's start with the game of Go. Just if you never played it, you don't have to understand the rules completely. Basically, the game is played by two players, just like chess, with white and black stones, just like checkers. And each player puts a stone on the board one by one on the intersections of these black lines. And the way the aim of the game is to have as many stones on the board by the end of the game once the whole board is full, to have the most stones on the board, which means in order to win you need to remove your opponent's stones. And the way you do that is by encircling them. So if you get something like this, here black gets to remove all of these white stones from the board. These positions are then stay vacant. So the idea is simply to try and create these little encirclements. And what happens when you play Go is that you think, oh, I'm starting to make a nice encirclement, and suddenly you find out that your opponent is encircling you. So it's this kind of weird switch around. So that's all you basically need to understand about the game. There are a lot of claims about why AlphaGo is so brilliant and why the game is so difficult. So not all of them are quite correct. You actually heard some of them in the trailer. So I'd like to go through them one by one. First to show a little bit of skepticism to counter all this hype. AlphaGo is an important move towards general-purpose AI. You heard this in the trailer. The techniques that are powering AlphaGo will power humanity, or whatever they said. So in some sense, it was a big step forward for reinforcement learning and a big step forward for neural networks. But other than that, AlphaGo itself is just a system designed for playing Go and not for anything else. So, and very much purpose-built for playing Go. And even to get it to play chess, you have to make some quite drastic changes. So the idea is that DeepMind built a system and the system figured out how to play Go, as I think the trailer hints, and that's a little bit misselling the point. They built a system to play Go, which was a very difficult problem and it was very tricky. So well done, but they haven't built anything towards general purpose AI whatsoever. AlphaGo thinks and learns in a human way. Well, you need to be a Go expert to derive this from the way it plays. From what I've seen in the movie especially, it plays in a very non-human way, which is why it was so difficult for Lee Sedol to play it very well. It's built on these neural networks, which are very vaguely inspired by human brains, but as you've hopefully understood, not that much. But it does learn through reinforcement learning. So it does learn through playing other Go players and playing itself. So that at least is something, one step better than offline machine learning. So mimics the human brain, forget about it. I mean, they're called neural networks, but there's nothing neural or networky about it. This is also something that's interesting. Go has more possible positions than there are atoms in the universe. That's why it's difficult. So certainly I agree with the first part. The problem is that's also true for chess, and also true for checkers. And checkers was solved in the 80s, and chess was solved in 2001, I think, when Deep Blue beat Kasparov. So it's true, but that's not why it's difficult. That's not why Go is so much more difficult than chess. And Go took us 20 years longer to beat than chess. Also, what you hear more often, which is slightly closer to being correct, is that what makes Go difficult is the high branching factor, which is the number of possible moves. If you look at the board, there's 19 times 19 possible places to put a stone. So there's something like 360 possible moves at the start of the game. So if you imagine the game is a tree, like I drew earlier, the first node of that tree has 360 children. So that's part of what makes it difficult. You cannot search through this exhaustively. Even one step is difficult to search through exhaustively. That's not just what makes it difficult. What makes it difficult is that you have this high branching factor, and you have this reward that comes very late. So you can imagine if we're starting, for instance, if we are starting a battle, I'm playing you, and I put down a white stone, you put down a black stone, and we're trying to encircle each other, we get a sort of line down the middle of the board, where we're just putting stones next to each other along the diagonal. And somewhere here we get the payoff. So you need to look ahead, you need to sort of predict that once we start doing that, oh, that's going to lead us to that corner of the board. So not only do we have a high branching factor, we need to look very deep into the tree to see the payoff. So you need to search very deeply, and you have a high branching factor. So you need to select, when you're searching a game tree, you need to select very cleverly, which nodes you're even going to explore, which nodes you're even going to look at. And if we're playing here, you need to realize that looking at this node is absolutely pointless, for instance. So that's what makes Go difficult. And it is very difficult, and until it was solved, nobody thought it was going to be solved for another 20 or 40 years. And for a long time, it was sort of held up as one of the most difficult games to solve in AI. And the thing to realize about games like this, go back one, is that before AlphaGo, nobody really was actually solving them using machine learning. So now it's very obvious, AlphaGo and DeepMind, blah, 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 so we should all use machine learning for this, and we should all use reinforcement learning. But before this, almost nobody was using machine learning to attack games like chess or checkers. So Deep Blue, for instance, with Kasparov, didn't use any machine learning, just search, just tree search. Nor did Stockfish, I think, which was then became the big chess engine, didn't use any machine learning. Only when people started attacking Go in this way did we realize that machine learning could be a really big help. So to explain AlphaGo, the first thing I need to explain are a couple of tree search methods that work well and that were developed before we started attacking things with machine learning. So this is just basic game tree search, which doesn't have that much to do with learning from data or learning from examples. This is basically how you build a chess engine. It's called Minimax. If you followed Intelligent Systems last year, you know how this works. If you followed another AI course, you may know how this works. I won't go into the details, but basically you search the whole tree, or at least for as deep as you can, and then you label each node with how likely the black or the white player is to win. We stick to a two-player game. And then you propagate up these values. So here the maximizing player, so we have two players, one player chooses the maximum values, the maximizing player puts the highest value, the minimizing player chooses here, so it puts the lowest value on this node that it can reach. Here the maximizing player, chooses, so it puts the highest value on there. You bubble up all the way to here, and then you just pick the highest node if you're the maximizing player, or the lowest node if you're the minimizing player. So I don't really have time to explain it properly, but basically this is how, if you have the time to exhaustively search the tree, or to exhaustively search the tree up to a certain depth, then you can use the Minimax algorithm to do this. It doesn't work for Go at all. It's a complete non-starter. So with chess you can sort of do this probably up till depth 20. With Go, maybe 1 or 2 moves at the most. So the first very simple idea that really made a dent in Go was the idea of using rollouts. It's a very simple idea, where you just take a very simple policy, so a function from states to moves, a move selecting function, something very simple that you can execute very quickly. Could be just random, a random move selection. And what you do is you do a rollout with it. You make sure that it's so fast that you can just go from the starting node of your game tree, you pick random moves, all the way down to a state where you've either won or lost. And you do that a few times. You average that for every next state that you're choosing. You do 50 rollouts, and you compute how many did I win. And then you move to the state where the most rollouts won. So you use a rollout as a kind of value estimate of your value function. How good is this state? How likely am I to win from this state? And then you move to the state that maximizes that value function. That's a rollout. Then came Monte Carlo tree search, which is a little bit more complicated. Basically, you start with an empty node, which is your starting state. Oh, yes. Yeah, that's a good question. So the question is, if you do rollouts, you need to also, your opponent needs to move as well. So these are your move, your opponent's move, your move, your opponent's move. Usually you just assume that your opponent plays the same policy as you do. So you just have some policy which is as good as you can make it, but fast enough that you can reach the bottom. And you just assume that your policy makes the same move, your opponent makes the same moves, or follows the same policy function. So Monte Carlo tree search. Basically, you start with your starting node, which is this current state, the board as it is. And then you have below that all the moves you can make and all the states you can reach by making those moves. You pick a random one, and you do a rollout. And then on this node, you put how many of the rollouts you want. So let's say we lost this rollout, then we won 0 out of 1 rollouts. Then you pick again, proportional to the probabilities on the nodes. So this now gets a low probability. Let's say we pick this one, we do a rollout, here we get 1 over 1. We do a couple more rollouts. Let's say we get 2 over 5 here and 4 over 5 here. And at every time you pick a node, you do 2 things. You expand the node and then you do a rollout. So if we pick this node, we expand it into its children, we pick a random child, and then we do a rollout. So then what we get here is we get 0 over 1 or 1 over 1. Let's say 1 over 1 here, we won this rollout. And we also update all the nodes above this. So now we did 1 more rollout, so the 5 becomes a 6. And we won it, so the 4 becomes a 5. So now from this node, below this node, we won 5 over the 6 total rollouts we did. Essentially, starting from this half-filled-in tree, you get 4 steps: selection, expansion, simulation, and backpropagation. Selection is just following the current probabilities you have on the nodes to select one of the leaf nodes. Expansion is expanding the leaf node into its children by picking a random child. Simulation is doing a rollout from that child. And backpropagation is updating all the nodes above this child by increasing the number of rollouts by 1 and increasing the number of rollouts 1 also by 1 if you won the rollout. So if you keep doing this, you get an expanded subtree with probabilities on the nodes that indicate how likely you are to win from those nodes. That's MCTS, Monte Carlo tree search. And it's one of the first algorithms that really made that could basically beat an amateur player at Go, I think. But not any kind of professional. So this was sort of the state of the art when AlphaGo came in. And AlphaGo, basically, their whole idea was to say, we're going to do deep reinforcement learning and apply it to Go. So we're going to train a neural network to play Go for us, and we're going to train it using reinforcement learning. So they trained 2 basic neural networks. A policy network, which takes the board, passes it through several convolution layers. Basically, if you look at a Go board, it looks like an image. They look like pixels, right? Black and white pixels. So you can use a neural network that is suitable for images, namely a convolutional neural network. You pass this through several convolutional neural network layers, and the policy network simulates a policy function. So its output is a probability distribution on moves. So in this state of the board, these are the likely moves. These are the moves that are likely good. And the value network simulates this value function, which says, from this state, again, it takes a state, a board, from this state, how likely am I to win? Give me a probability that from this state, the black player is going to win. So there's just one sigmoid node that's on the output, which gives us a probability. So we have these two networks. And actually, let me say it properly. So the we start with, in the original AlphaGo, we start with SL, which is a policy network which is trained on a database of human moves. So you can just go through a database of existing Go games and then just do supervised learning of this. Okay, so the question is, if AlphaGo is trained with human moves, how well would it perform against another machine learning algorithm? Are you saying if it's just trained with human moves, or? Yeah, I think you're right. So you're probably right that if you trained it only with human moves, so you use only supervised learning, it wouldn't probably play more like a human being. So it would sort of simulate how an average human being would play. I have no idea what the quality would be, whether it would beat a machine learning player or whether it would. I have no idea. Presumably they didn't publicize, presumably they tried it and they didn't do anything with just that version of AlphaGo, so presumably it doesn't work that well. But just to finish my thought here, they start with a value network. No, sorry, a policy network trained on a big database of human moves. Just no reinforcement learning, just supervised learning. If you're in this state, you should do this. Trying to predict what a human player would do. Then they start with that network and they update it using reinforcement learning. So they play against versions of itself and update using policy gradients. And they actually train a slow version and a fast version because we're going to do rollouts later, so they need a fast version to do rollouts and a slow version to do early search, early in the game tree. And then you have a value network, which is trained also during this self-play, by recording this self-play. So then we have these two networks. And if you play just with these, so you can play with these directly, you can just ask the network, what should I do? And then move, and then you get a reasonable player, but not world standard. So what you do then is you plug these networks into a Monte Carlo tree search, which is quite a complicated, especially in the original AlphaGo, it's quite a complicated version of Monte Carlo tree search. So I won't explain all the ins and outs. But essentially, you use the basic Monte Carlo tree search principle together. You mix it with one of these policy networks to search, to open up these nodes. And once you open up the nodes, you use the slow policy network to move the first couple of nodes, the fast policy network to move the rest of the nodes all the way down to a winning or losing state. And then you propagate back up. So this is a kind of like the simple Monte Carlo search algorithm I showed you earlier, but with all these networks mixed in a slightly ad hoc and slightly inelegant way, probably because they needed to beat least at all, so they were trying just whatever works. So that's basically the first generation of AlphaGo. And what they did then last year, you may have seen this in the news, they came up with a version that didn't use this human knowledge. So they didn't use this human database of human moves. That started with a clean slate neural network, played only against itself, no human intervention, no watching humans play Go, and then turned out to work much, much better than the original AlphaGo. So let's, basically they used 3 tricks to improve the original AlphaGo, to create AlphaGo 0, this new version, which had no background knowledge, essentially. So let's go through those 3 tricks. First, they combined the policy and the value net into a single network, which they called the two-headed beast, or the two-headed monster. Basically, this is turned around from the way I normally draw neural networks, because I took this from the paper. So the input is here, the output is here. So you get a single input for the board state. The board goes into the neural network, goes through some convolutional layers, and it splits into 2 outputs. One output is a policy output, so distribution over states, distribution over actions. And the other is the value. And the advantage here is that these layers get more information, get more gradients, because they get gradients from both training the policy and training the value, which we'll look into later how that happens. So they get these weights here get much more information, and they can learn a more general representation of the board, from which you can derive both the policy and the value. So this works much better. Second trick, which is probably the most important trick, is that they view Monte Carlo tree search as what they call a policy improvement operator. Essentially, if I'm doing Monte Carlo tree search, I do so with a policy, right? I use some policy to do these rollouts. And after a few steps of MCTS, what I get is a policy or a value network. So these are values, and if I pick the follow-up state with the highest value, I get a policy. So after I do a bunch of updates with this Monte Carlo tree search, I get a new policy. So I can turn one policy into another policy, or I can turn one value function into another value function, where the second is always better. So if I start with some poor policy function, I put it through MCTS, I get a better policy function. If I start with a random policy, which just picks random moves, but I do a huge amount of MCTS search, so I do basically infinite MCTS search, I still get the optimal policy. If I start with a very good policy and I do a little bit of MCTS search, I get a slightly better policy. So the basic idea here is that if you do this, if you start with your policy that you already have, you do a bit of MCTS search, you get a new policy, you can use that as a training example. You're saying, so this is the policy that my neural network outputs now if I just feed it the state. I do a bit of MCTS, I get another policy, which I know is better, because I've used the policy improvement operator. That means I can tell the neural network, this is what you outputted, this is what I want you to output. Compute the difference, compute the gradient, and backpropagate. So this is what AlphaGo 0 did. They play a game against some opponent. They observe the output after MCTS, and then they give that back as a target for the network. And that's how it trains the networks. That's how it does self-play, essentially. That's much more simple than the original AlphaGo. And then trick 3, which isn't really relevant for this lecture, but I thought I'd mention it anyway, is they added residual connections, which is not a reinforcement learning trick or a Go-specific trick. It's just a very common neural network trick, where basically if you have a bunch of layers, if you want to train a very deep neural network and you have a bunch of layers, it helps to create a connection, a so-called skip connection, which takes the input and skips those layers. So the input goes through the layers and gets transformed, but it also gets passed next to the layers, multiplied by some learnable value A. This is a weight. This is learned. And the result is the value that is passed through the layers plus the skipped value. So the idea is that at the start of training, you're basically ignoring these layers. You have a shallow network. These layers aren't used and A is set to 1, and this is just passed through. And then as your network gets more complicated, as it gets more deep, as it were, as you get more need for depth, this skip connection shrinks and more information starts pouring through the layers. And this is especially useful when you think about the gradient. So the gradient can now, during the start of training, the gradient can move through this skip connection all the way to the earlier layers, where during the beginning of training, it's important to have strong gradient, strong error information. So this worked very well for them. That was the third trick. These three tricks together worked very well for them. And this is how AlphaGo performed. So this is days of training, and training on quite a sizable cluster. So they have, in total, 5,000 TPU units, which are sort of Google's equivalent of GPUs. So probably about 2,000 machines at least. But nevertheless, they trained on that. And at around the 30-day mark, or what is it, 25, AlphaGo 0 overtook the, already at 4 days it overtook the AlphaGo which you saw in the documentary trailer, which beat Lee Sedol. Then by that time they had already trained a better version of AlphaGo called AlphaGo Master, which was playing online. And that it overtook in about 30 days. Then they had a version of AlphaGo trained entirely on self-play with no knowledge about the game other than its rules, which was better than any human player probably will ever be. Basically, this represents 2,000 or 3,000 years of human development in Go playing, and after 4 days, it just beat that. And it's an ELO rating of 1,000. That's just so high. You're never gonna beat that. Never gonna beat that at all. And then in the same year, they pre-published some work where they adapted AlphaGo to play chess and to play a game called shogi, which is a kind of Chinese, I think Japanese chess. Stockfish is a system that is based on uses the basic principle of Deep Blue, so basic search, no machine learning, basic tree, very clever tree search. And it's, well, up until a year ago, it was by far the best, it was the best chess playing system in the world. So they played against that, and as you can see, after, well, 200,000 steps, I think it was about 4 hours on this massive cluster. 4 hours of training, it started to beat Stockfish. It should be mentioned that the training takes a big cluster, takes 5,000 TPUs. Once you have the neural networks, you can play chess on a machine with 4 TPUs. So not on my laptop, but still on a single machine with a bit of hardware. You can play chess like this, or Go, or shogi. And here's the AlphaGo again. So this is Alpha 0 playing Go. It's slightly different from AlphaGo 0, but the details don't matter. So that's one of the most famous stories in machine learning and in general AI from the last couple of years. It was worth their while because shortly after they did this, they were taken over by Google for about $500 million. So it was a bit of an investment, but it works out in the end. And that's the last thing I wanted to teach you about machine learning. Before you get up, so next Thursday there's one more lecture where I will review everything we've talked about. I said this already, but I'm going to say it again. If you have any questions, email them to me and I will discuss things during Thursday's lecture. So thanks for your attention, and I will see you on Thursday.